Okay, let's have a look at the next question. This is to do with the contact process where you react sulfur dioxide with oxygen, forming sulfur trioxide, and you use a catalyst which is vanadium oxide, V2O5. You can see it listed here in the top. So let's look at this part C, a mixture of 96 grams of sulfur dioxide. And again, this is where this is slightly different because what you actually have here is grams. 96 grams of sulfur dioxide, 24 grams of oxygen. We've got a 50 litre equilibrium thing. Now, at equilibrium, we have 112 grams of sulfur trioxide. So there are main details. The first thing we're asked to do is write the equilibrium constant, Kc, for the expression. So that's always the easiest one, and it's handy marks. So we start with Kc. So again, what's on the right-hand side of the equation goes on top. So we've got SO3. And we can see from the equation that it is 2SO3, so that means we have to put a power of 2 up there. On the left-hand side, we've got an SO2, again in square brackets to indicate concentration, and there's a 2 up there as well because of the 2 here. And we also have to put in O2. In order to do this, we've got to transfer everything into moles. So we're going to take our grams of sulfur dioxide, our grams of oxygen, and our grams of sulfur trioxide and convert them into moles. So let's have a look at that. We've got 96 grams of sulfur dioxide. We have 24 grams of oxygen. And we have 112 grams of sulfur trioxide. So 96 grams of SO2. So working at the molecular mass of sulfur dioxide, well, sulfur is 32. So sulfur is 32 plus 2/16 for oxygen. That gives you a total of 32 and 32, which is 64. Now, for your Leaving Cert, you don't have to show this addition. However, if you don't show the addition and you make a mistake, you're going to lose marks. So it's important that you actually show your addition for each of this. I'll just do it for this example. I'll skip it for the other ones, but you know what you have to do. So again, to find out the number of moles of this, you're going to go with 96 grams. You're going to divide by the molecular mass, divided by 64, and that's going to give you 1.5 moles. You do the same thing, 24 grams of oxygen, so 24 grams. And again, that's going to be divided in this case by 32. Which gives you 0.75 moles. And then 112 grams of sulfur trioxide, so that's going to be 112 grams divided by, and sulfur trioxide will work out at 80. And then that gives you 1.4 moles. So now you have the details. You can go fill them in to your equilibrium mixture. So I'll come back in a second when we have that done for the table. Okay, so we have our table drawn here. Let's put in our details for the equations. So we have got 2 SO2, we have an O2, and then we have our equilibrium and 2 SO3 on the right hand side. And to work out what we've got initially, we've got to go back to the question. So we're told that a mixture of the sulfur dioxide, so this here is your sulfur dioxide. This here is your oxygen. So we have 1.5 and 0.75 moles. And then at the very end, it tells us this bit. At equilibrium, 112 grams of sulfur trioxide. Now we've actually worked out that 112 grams as 1.4 moles. So that's what we had at equilibrium. This one here is at equilibrium. So we can put these numbers in. So let's start off. So initially we had 1.5 of the sulfur dioxide. We had 0.75 of the oxygen. And initially we had 0 of this. At equilibrium we had 1.4 moles of this, which means there is an overall gain of plus 1.4. Now where do we go from here? How do we try and figure this out? Well, there's a couple of things that you have to be always careful with. When you're working out this equilibrium calculation, we have to look at the numbers that are in the front. Normally, if it's a 1:1, you will put the same numbers in beside each other. In this particular example, we have a 2 on the left-hand side here, and we also have a 2 on the right-hand side here. So if 1.4 has increased here, you're also looking at 1.4 here, purely because the number of moles are the same. There are other ways of doing this, but that's the way I tend to work with it. Now, if you bear in mind that this first one here is a 2:1 ratio in terms of the number of moles. If this is minus 1.4, and we got that from this one here on the right, then that means that the oxygen, if this is a 2:1, is going to be half of this minus 1.4, which is minus 0.7. Once we have these two details, we can fill in the rest of the equilibrium. So this one here is going to be 0.1 when we do this calculation. And when we do this calculation here, we're going to get 0.05. And we have our 1.4. Now again, going back, let's check our 50 litre. It is. There's your 50 litre. So we can go back down and write that in. We have a 50 litre container. So again, we're going to have to divide across by 50. So dividing by 50. That's going to give you some numbers. So let's say I have them here. So that is going to give you 0.002. This one will give you 0.001. And then this last one here is going to give you 0.028 when you divide across by 50. So this here is at equilibrium, but that's at a 1 litre vessel. Okay, so now we've got to take these numbers and pop them into our Kc equation. Let's just make a bit of space. So again, working with our Kc equation, and the Kc equation is up here. There's the details. So we're going to just pop them into that equation there. So it should be straightforward from here. 0.028 squared. Move that up so you can see the numbers. All divided by 0.002, and that's squared, and that's multiplied by 0.001, and that gives you a final number of 196,000. And again, you should write that into scientific notation, which is going to give you 1.96 multiplied by 10 to the 5. And you have to put it in the form a multiplied by 10 to the power of n, where a is less than or equal to 1, less than or equal to 10. So this is your final answer. Okay, so let's keep going with 2015. Table is here. We've got A, B, and C, and we're going to try and fill in some numbers. So looking at the first part of it here, we've got, let's put this in here. So the first thing we've got is, well, we have a 10 litre container. That's the first thing to be careful of. Now we have 30 moles of gas A. So this is initially. So this is something we can figure out. It also tells us that the equilibrium constant is 4.0. So that's something we're going to need. So at the start, we know that Kc is already 4 or 4.0. Let's fill in our initial value. So our initial values is, well, 30 litres of gas A. That means we have 0 at B, 0 at C at the very, very start. Now we've got to work out our change. Now in this particular example, it doesn't tell us anything about the change, and it doesn't tell us anything about what was left in the container at equilibrium. So what we're going to have to do is we're going to have to use X. So if we put something in, you're producing X amount of something. So when you put that in for B, again, this is a 1:1:1 ratio, so it makes the calculations a little bit easier. That means this must also have a plus X. And then over on this side, this is going to be negative X. So at equilibrium, remember this negative X, by the way, doesn't have to be plus X is 2X minus 2X. It doesn't have to be that. So at equilibrium, we have 30 minus X. And then over here, we've got plus X. And over here, we've got plus X. We also have a 10 litre vessel, so we've got to take that into account. So dividing across by 10, that means we're going to have 30 minus X divided by 10 for A. We're going to have X divided by 10 for B, and X divided by 10 for C. And that's what we're going to put into our calculations. Kc for the reaction is going to be Kc equals and our products go on the top, B multiplied by C in square brackets, all divided by the concentration of A. No powers here because everything is the power of 1, and if Kc is equal to 4, that means all of this is equal to 4. So if we do the maths down here, let's make a bit of space, and let's put them in. So what have we got? We've got, okay, so let's put those numbers into Kc. So we have B multiplied by C, and again Kc is equal to 4 here. So 4 is equal to, and then we've got B multiplied by C, so we've got x over 10 multiplied by x over 10, and that's all divided by A, and A is 30 minus x all divided by 10. So what's that going to give us? So now we've got 4 is equal to x squared over 100 all divided by 30 minus x all divided by 10. And what I'm going to do here is I'm going to bring that up there and to multiply it in. So we've got 4 multiplied by 30 minus x all over 10, and that equals x squared over 100. And again, depending on what way you want to do your maths here, there's lots of different ways you can figure this out. Just push this down, make some space. So I would also bring up the 100 here possibly as well. You can bring that 100 over. So you end up with 4 multiplied by 100 multiplied by 30 minus x all over 10, and that equals x squared. You can, if you want here, 10 goes into 110 times, if you want to do that. So 4 by 10 then is equal to 40, so you have 40 then multiplied by 30 minus x. So 40 multiplied by 30, that's going to give you 1200. And then 40 by minus x is minus 40x, and that equals x squared, or whatever way you want to do it. We've obviously got a quadratic equation here. So I'm going to bring that across, and I'm going to bring that across, and I'm going to be left with x squared plus 40x minus 1200 is equal to 0, and we're going to have to try and factorize that. So factorizing that, if you're unsure at this stage, of course you can do the minus b formula, but hopefully you should be able to figure out that 1240 is 60 and 20. So we've got 60 in one bracket, we've got 20 in the other, but of course we want to make positive 40, so that's plus 40, plus 60 and minus 20. So x has two values of minus 60 and x is equal to 20, but the one that we're interested in is of course the positive value. Okay, let's see if we have answered this question. So we'll go up to the top and we'll see the question is actually asking us calculate the number of gaseous moles at equilibrium in the container, so in total. So let's go back in here and see what we've got. So what is this x equal to 20? So this x equal to 20, and this is 20 moles, and this is B. We also know that C is also x, so we've got 20 moles C. But then also, what about A? Is there any of A left in the container? And if we go back up here, we can see that at equilibrium, there was 30 minus x present at equilibrium. So 30 minus x is going to be 30 minus 20, which is going to give us 10 moles of A. So not all of A reacted. So in total, you've got 50 moles total at equilibrium in the container. And that finishes off 2015. Time to move on to 2014, and that's probably going to be in the next video.